Good morning, everyone, or good afternoon, depending on where you are listening from. Welcome. My name is Dr. James Mitchell, and this is the first in what I hope will be a long series of lectures on how the universe actually works. Not how we wish it worked, not simplified versions that leave out the interesting parts, but how it genuinely operates, explained in a way that doesn't require a physics degree to follow. Now, let me tell you what to expect from these lectures. I'm not here to entertain you with flashy visuals or dramatic storytelling. I'm here to explain, to take ideas that might seem impossibly complex, fusion, gravity, entropy, space-time, and show you that they're not only understandable but deeply logical. You won't need any advanced mathematics. You won't need prior knowledge of physics. All I ask is that you think carefully and stay curious. A bit about the format. These lectures are designed to feel like what they are, university-level explanations, for people who are interested but not experts. I'll use analogies, lots of them, because they work. I'll occasionally check in to make sure the ideas are landing, and I'll assume you're intelligent enough to handle nuance without needing everything oversimplified. If something isn't clear, that's on me, not you. I'll try to explain it another way. Now, a few practical notes before we begin. These lectures are long, not because I like the sound of my own voice, but because real understanding takes time. You can listen while doing other things. Many people do. But the ideas are structured to build on each other, so if you skip around, some parts might not make as much sense. Feel free to pause, rewind, or come back later. There's no test at the end. The goal here is simply to understand a bit more about the reality we all live in. So, with that said, let's begin. Today's lecture is titled, Why Stars Exist at All. It's a foundational question, one that leads directly into chemistry, planets, life, and ultimately, us. By the end of this lecture, you'll understand not just how stars form, but why they had to form, why they're not optional, and why, without them, nothing interesting would exist in the universe. So settle in, get comfortable, and let's talk about stars. If you could travel back to the very early universe, you would probably be disappointed. There would be no stars, no planets, no galaxies, no light in the familiar sense at all. Just a vast, expanding darkness filled almost entirely with hydrogen, a bit of helium, and very little else. From a physics point of view, this was an elegant universe. From any other point of view, it was catastrophically boring. And yet, somehow from this simplicity came everything we see around us. Stars, planets, chemistry, biology, and eventually people capable of wondering how it all happened. So the question we're asking today is not how stars form. That part is well understood. Today's real question is more fundamental. Why do stars exist at all? Because as it turns out, stars are not just one of many features the universe could have chosen to include. They are something the universe was almost forced to create. To understand why, we need to start with an uncomfortable fact. The universe does not care about complexity. It does not care about life. And it certainly does not care about our desire for interesting things to exist. All it follows are a small number of very simple physical rules. And yet, those rules, followed relentlessly, make stars almost inevitable. So let's start at the beginning. In the beginning, after the universe cooled enough for matter to exist, there were only the simplest ingredients available: hydrogen, helium, and a tiny trace of lithium. That's it. Think of it like this. Imagine trying to build a house, but the only materials you have are 3 types of Lego bricks, all the same basic shape. No wheels, no windows, no specialty pieces. You could stack them, sure, but you're not building anything interesting. The early universe had the same problem. No carbon, no oxygen, no iron, no elements capable of forming rocks, oceans, or living cells. If the universe had stayed like this, chemistry would have stalled almost immediately. And without chemistry, nothing particularly interesting can happen. So the universe faced a problem. Not a problem in the human sense, but a physical limitation. How do you turn simple matter into complex matter? The answer begins with gravity. Now, before we talk about what happens inside stars, we need to understand what gets them started in the first place. And that comes down to one force: gravity. Gravity is, in many ways, the most patient force in nature. It is incredibly weak, but it never switches off. Here's a useful way to think about it. If you and I stood a meter apart, the gravitational attraction between us would be about 1/10,000,000th of the weight of a grain of sand. Pathetically weak. But gravity has one advantage: it never gives up. And given enough time, gravity has a remarkable habit. It takes things that are slightly uneven and makes them very uneven. Let me explain what I mean by that. In the early universe, matter was not perfectly smooth. Some regions were just a little denser than others, tiny fluctuations left over from the Big Bang. Gravity noticed. Imagine a crowded room where everyone is standing randomly. Now suppose 5 people happen to cluster near one corner, not on purpose, just by chance. That small cluster creates a slight pull. More people drift toward it, which makes the pull stronger, which attracts even more people. Soon you have half the room squeezed into one corner and the other half nearly empty. Gravity does exactly this, but with clouds of gas spread across light years of space. Over millions of years, those slightly denser regions began to pull in more matter, which made them denser still, which made gravity stronger. It's a feedback loop, a slow, inevitable one. Does that make sense so far? Excellent. Because here's where things start to get interesting. As vast clouds of hydrogen gas began to collapse under their own weight, something remarkable happened. They heated up. This is one of those unintuitive facts of physics. When you compress gas, its temperature rises. Think of your bicycle pump. When you push the handle down quickly, compressing the air inside, the metal barrel gets warm. You're not adding heat from outside. The compression itself generates the warmth. Now imagine compressing not a small tube of air, but a cloud of gas the size of our entire solar system, squeezed down to something the size of a city. The temperature doesn't just rise, it skyrockets. At the center of these collapsing clouds, temperatures climbed into the millions of degrees, and at that point, the universe crossed a threshold. Now, to understand the next stage, you need to know something about how atoms behave. Bear with me for a moment. This is important. Under normal conditions, atomic nuclei strongly repel one another. They're all positively charged, and those positively charged nuclei do not like being close together. Imagine 2 powerful magnets, both with their north poles facing each other. Push them together and they resist violently. Atomic nuclei do the same thing, but far more intensely. Under normal circumstances, they will never touch. But at extremely high temperatures and pressures, something changes. The nuclei are moving so fast, like cars on a highway traveling at thousands of kilometers per second, that when they collide, they don't just bounce off. They smash together with enough force that occasionally they get close enough for a different force to take over. The strong nuclear force. Let me give you an analogy that might help here. Think of it this way. Electric repulsion between nuclei is like 2 magnets pushing each other away. But if you can force them close enough, within a tiny, tiny distance, a hidden Velcro layer suddenly grabs them and locks them together. That's the strong nuclear force. It only works at incredibly short range, but when it activates, it's far stronger than the electric repulsion. When that happens, two hydrogen nuclei fuse together, and when they do, a small amount of mass, a truly tiny amount, is converted into energy. That energy is released as light and heat. A star turns on. All right, so that's how stars begin. But what keeps them going? That's what I want to talk about next. A star is not a simple object. It's a battlefield. On one side, you have gravity, constantly trying to crush everything inward, pulling the star toward collapse. On the other side, you have the energy released by fusion, pushing outward, trying to blow the star apart. Think of it like an incredibly tense tug-of-war. Two teams of equal strength, pulling in opposite directions. Neither side wins. The rope stays perfectly still in the middle. That's what a star is. For millions, sometimes billions, of years, gravity and fusion pressure balance each other almost perfectly. The star doesn't collapse. It doesn't explode. It just shines. This balance is called hydrostatic equilibrium. It's a term that sounds complicated, but it just means the inward squeeze equals the outward push. And as long as that balance holds, the star remains stable. Now, I want to focus for a moment on what's actually happening in the core, because this is where the universe starts building its periodic table. At first, stars only fuse hydrogen into helium. Two hydrogen nuclei combine to make one helium nucleus. In the process, a tiny bit of mass disappears and becomes energy, light and heat. This is the fuel that keeps the star shining. But here's the thing. Stars are not efficient. Think of a star like an old coal furnace in a Victorian home. It burns fuel continuously, day and night, just to keep the house warm. But eventually, no matter how much coal you started with, you run out. Stars are the same. For a star like our Sun, the hydrogen fuel in the core will last about 10 billion years. That sounds like forever. But it's not infinite. And when the hydrogen in the core runs out, the star faces a crisis. So what happens when the fuel runs out? Well, this is where things get dramatic. When the core runs out of hydrogen, fusion stops. No fusion means no outward pressure. And without that pressure, gravity wins the tug-of-war. The core begins to collapse. Now remember what we said earlier. When you compress gas, it heats up. So as the core collapses, it gets hotter. Much hotter. Hot enough that something new becomes possible. The helium nuclei, which were just sitting there as the ash left over from hydrogen fusion, can now fuse together. Let me put that another way. Imagine you've burned all the wood in your fireplace. You're left with charcoal. Normally, charcoal is just leftover waste. But if you make the fire hot enough, the charcoal itself can burn. That's what happens in a star. When the core gets hot enough, helium starts fusing into carbon and oxygen. The star reignites. But this time, the fuel burns hotter and faster, and this brings us to one of the most dramatic phases in a star's life. This is when stars enter what astronomers call the red giant phase. The core is now fusing helium. But the outer layers of the star, the hydrogen-rich shell around the core, also start fusing in a shell surrounding the core. With two fusion zones active, the star produces far more energy than before. That energy pushes the outer layers outward. The star swells. It becomes enormous. Our Sun, for example, will one day expand to roughly the orbit path of Earth. It will engulf Mercury, probably Venus, possibly even us. But here's the strange part. Even though the star is now bigger and brighter, its surface actually becomes cooler. Think of stretching a rubber band. As you pull it wider, the material gets thinner. The outer layers of a red giant are spread so thin that they cool down. That's why they glow red instead of white or blue. Cooler surfaces emit redder light, so the star becomes a red giant, huge, bright, but with a relatively cool surface. The nearest red giant to us, Arcturus, sits about 37 light-years away, a star that has already swollen to more than 25 times the size of our Sun. It's actually one of the brightest stars in our night sky. Now, you might be wondering, what happens when the helium runs out? Good question. For stars like the Sun, medium-sized stars, this is basically the end of the road. The core collapses one final time, but it never gets hot enough to fuse carbon and oxygen into anything heavier. The star sheds its outer layers in a beautiful, glowing shell called a planetary nebula. Not because it has anything to do with planets. Early astronomers just thought they looked planet-like through their telescopes. At the center, what's left is the collapsed core, a white dwarf. Think of a white dwarf like this. Imagine compressing the entire mass of the Sun into an object about the size of Earth. No fusion happening anymore, just a dense, hot ember slowly cooling over trillions of years. That's the Sun's fate. It will shine, swell, shed its outer layers, and leave behind a white dwarf, a stellar tombstone. But not all stars die this quietly, and this is where things get really interesting. Larger stars, those with at least 8 times the Sun's mass, have a very different fate, because when they run out of helium, they don't stop. Their cores are massive enough that when they collapse, they get hot enough to fuse carbon, then oxygen, then neon, then magnesium, then silicon. Each stage produces heavier elements and burns faster than the last. Think of it like a candle with layers. The outermost layer burns slowly for hours. The next layer burns in minutes. The core burns in seconds. By the time a massive star reaches the silicon-burning stage, it has only days left to live. And here's the crucial part. Each fusion stage releases less energy than the one before. Fusing hydrogen into helium releases a lot of energy. Fusing helium into carbon releases less. Fusing silicon into iron releases almost nothing. And iron is the end of the line. Now let me explain why iron is so special, because this is one of the most important ideas in all of stellar physics. Fusion works because when light nuclei combine, they release energy. That's what powers stars. But iron is different. Iron nuclei are the most stable nuclei in the universe. Fusing iron into something heavier doesn't release energy. It requires energy. Here's a way to think about it. Imagine fusion as walking down a staircase. Every step down releases a little energy, like dropping a book from one step to the next. The book falls, and that releases energy you could capture. Hydrogen fusing into helium? That's stepping down. Helium into carbon? Another step down. Carbon into oxygen, neon, silicon, down, down, down. But iron is the ground floor. There are no more steps below it. To make something heavier than iron, you'd have to carry the book back up the stairs. That costs energy. You have to do the lifting. Stars don't have energy to give. They're already using everything they generate just to stay alive. So when the core turns to iron, the staircase ends. Fusion stops, gravity wins. The core collapses. And what happens next is one of the most violent events in the entire universe. This is not a slow, gentle collapse. This is catastrophic. The core of the star, an object about the size of Earth but with more mass than the Sun, collapses in less than a second. Imagine a building the height of Mount Everest collapsing to the size of a football field in the blink of an eye. That's the scale of violence we're talking about. The collapse is so sudden and so violent that it creates a shock wave. That shockwave rips through the outer layers of the star and blows them into space at a significant fraction of the speed of light. This is a supernova. For a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. It is one of the most energetic events in the universe. Now here's why all of this matters. And this is the key point I want you to take away from this section. During a supernova, the extreme conditions, the heat, the pressure, the density, are finally enough to create elements heavier than iron. Gold, platinum, uranium, all the heaviest elements in the periodic table. They're not made in the calm, steady fusion of a star's core. They're made in the final, violent seconds of its death. Think of it this way. Stars spend millions of years carefully building elements up to iron, like a patient craftsman. Then, in their death, they smash everything together with such force that the entire upper half of the periodic table is created in moments. It's like spending years building an intricate house of cards, then setting off fireworks inside it, and somehow, in the explosion, creating diamonds. Feel free to pause for a moment and consider what this means. Okay, let's continue. After the explosion, all of those newly created elements, carbon, oxygen, iron, gold, are scattered into space. They mix with clouds of hydrogen and helium, and eventually, those enriched clouds collapse under gravity to form new stars and planets, and on at least one planet, life. This is where you come from, not metaphorically, literally. The calcium in your bones was created in a star that lived and died before the sun was born. The iron in your blood was forged in a supernova explosion billions of years before the Earth existed. The oxygen you're breathing right now was made in the core of a massive star. You are not made of stardust in some poetic sense. You are literally assembled from the remnants of dead stars. All right, so now I want to step back and look at the bigger picture. Because the question isn't just how do stars work, it's why do stars matter? Here's the answer. Without stars, the universe would be stuck. Remember, after the Big Bang, the universe had only hydrogen, helium, and a trace of lithium. That's it. 3 elements. You can't build much with 3 elements. You certainly can't build planets. You can't build water. You can't build DNA. To get from that simple early universe to the rich and complex universe we see today, something had to create new elements. And the only way to do that is fusion. But fusion requires extreme temperatures and pressures, which means you need gravity to compress matter, which means you need stars. Stars are the universe's only mechanism for turning simple matter into matter more complex. There is no alternative. Without stars, chemistry stops at helium. Without chemistry, there are no molecules. Without molecules, there is no biology. Without biology, there is no one around to wonder why the universe exists. Stars are not optional. They are the necessary bridge between the simplicity of the early universe and the complexity of everything that came after. Now, here's what I find truly remarkable about all of this. None of this required a plan. The universe didn't decide to create stars. It just followed the rules. Gravity pulls the matter together. Compression heats gas. Heat enables fusion. Fusion creates new elements. Supernovae scatter those elements. New stars and planets form from enriched material. Each step follows inevitably from the one before. It's like watching dominoes fall. You don't need a cosmic designer arranging each piece. You just need the first domino to tip. In this case, gravity acting on slightly uneven matter. and the rest unfolds automatically. Let's picture that in a slightly simpler way. Imagine you have a box of marbles on a tilted table. You don't need to tell the marbles to roll. You don't need to guide them. Tilt the table and they roll on their own, not randomly, but following the slope, the friction, and the shape of the surface. The universe is the same. It's not random. It's not chaotic. But it's also not designed in the way we usually think of design. It's something in between. Structured emergence. Stars are what happens when the universe runs its program, and we are what happens when stars run theirs. Before we wrap up, I want to talk about time for a moment, because one of the most important things to understand about stars is just how patient they are. Our sun has been shining for about 4.6 billion years. It will continue shining for another 5 billion years or so before it runs out of hydrogen and becomes a red giant. That's a total lifespan of roughly 10 billion years. To put that in perspective, the entire history of human civilization, from the first cities in Mesopotamia to today, is about 10,000 years. The sun has been shining for 460,000 times longer than that. When the sun first ignited, Earth didn't exist yet. When it dies, Earth will likely be gone. Stars operate on timescales so vast that human history is barely a blip. But here's something to keep in mind. Not all stars live the same length of time. Massive stars, the ones that create supernovae, burn their fuel far more quickly. Think of it this way. Imagine a pair of people with different amounts of money. Person A has $1,000 and spends one of those dollars per day. Person B has $10,000 but spends 100 of those dollars per day. Who runs out of money first? Person B. Even though they started with more, they're spending it faster. Stars are the same. Massive stars have more fuel, but they burn it at a furious rate. A star bearing 20 times or more mass of the sun might live only a 10 million year life. That sounds long, but it's nothing compared to the sun's 10 billion year lifespan. The largest stars live fast and die young, brilliant, violent, and short-lived. Smaller stars like red dwarfs can live for trillions of years, far longer than the current age of the universe. In fact, every red dwarf that has ever formed is still alive today. None of them have had time to die yet. And this raises an interesting point. The universe is currently about 13.8 billion years old. That's old enough for massive stars to have lived and died many times over. But it's not old enough for stars like the sun to have completed their life cycles, which means that almost everything we know about stellar evolution, the red giant phase, white dwarfs, the final fate of medium-sized stars, is based on theory and observation of other stars, not our own. We've never watched a star exactly like the sun die, because none of them have died yet. But we've watched enough stars of different masses and at different stages that we can piece together the full story. It's like watching a forest. You don't need to follow a single tree from seedling to death. You look around and see seedlings, young trees, mature trees, and fallen logs. From that, you understand the life cycle. We do the same with stars. There are more similarities between life on Earth and the workings of the universe that we tend to overlook. So we've talked about why stars begin. Now let's talk about why they end, because the death of stars is just as important as their birth. Maybe more so. Here's the key idea. Stars run out of fuel. That might sound obvious, but it has profound consequences. Because when a star runs out of fuel, it doesn't just fade away quietly, it transforms. Medium stars become white dwarfs. Massive stars become supernovae, then neutron stars or black holes. And in doing so, they fundamentally change the chemical makeup of the universe. Think of it this way. The early universe was like a pantry stocked with only flour and water. You could make bread, maybe some simple pasta. but you couldn't make a birthday cake or a stew or anything complex. Stars are the chefs that take those basic ingredients and, through heat and pressure and time, create new ingredients. And when they die, they scatter those ingredients back into the pantry. So the next generation of stars and planets has access to a much richer set of materials. And this is crucial for understanding where we came from. The Sun is not a first-generation star. It formed from a cloud of gas that had already been enriched by earlier generations of stars. That cloud contained carbon, oxygen, silicon, iron, all the elements needed for building rocky planets like Earth. If the Sun had been a first-generation star made purely of hydrogen and helium, it wouldn't have planets, or at least not planets like ours. You might get gas giants, massive balls of hydrogen, like Jupiter, but no rock, no metal, no water. The Earth exists because earlier stars died. Every rock you've ever touched, every mountain, every grain of sand. It's all recycled stardust. And not just from one star, from dozens, hundreds, maybe thousands of stars that lived, died, and scattered their elements before the Sun was born. We are the descendants of a cosmic recycling program. So let's zoom out one final time. Because the story of stars is really the story of how the universe becomes interesting. At the beginning, you have simplicity. Hydrogen, helium, smooth expansion, no structure, no complexity, nothing to look at. Then gravity starts pulling matter together. Stars ignite, elements are created, stars die. Elements spread. Brand new stars form from enriched material. Planets condense from the debris. Chemistry becomes possible. Molecules form. And eventually, on at least one planet, molecules arrange themselves into something that can replicate, evolve, and think. Stars are the reason complexity exists. Not because they intended to create complexity, but because their existence made it possible. There's a term in physics that I think captures this beautifully: emergent complexity. It means that simple rules, followed over time, can produce extraordinarily complex results. You don't need a complex starting point. You just need time, iteration, and a few basic forces. Stars are a perfect example. You start with gravity and gas. That's it. No intelligence required, no guidance needed, just physics. And from that, you get fusion, new elements, supernovae, planets, life, consciousness. Each layer builds on the one before, naturally and inevitably. It's not random, but it's also not designed. It's something stranger and more elegant, structured emergence. So, to come back to the question we started with, why do stars exist at all? They exist because the universe had a problem. It started simple, much too simple to do anything interesting. And the only way to move from simplicity to complexity is to build new elements. The only way to build new elements is fusion. The only way to achieve fusion is extreme heat and pressure. The only way to generate that heat and pressure is to compress massive amounts of matter. And the only force capable of doing that is gravity. Put it all together and stars aren't just likely. Given the laws of physics, given the initial conditions of the universe, given enough time, stars had to form. Not because anyone wanted them to, but because the universe, in a sense, had no other choice. And once stars existed, everything else followed. Planets, chemistry, biology, thought. We exist because stars exist. And stars exist because our universe is governed by a small set of rules that, when followed long enough, make complexity not just possible, but unavoidable. That's the real answer. Stars are not accidents. They're not miracles. They're the natural, predictable consequence of a universe running its course. And, in a way, is far more beautiful than any design could be. because it means the universe doesn't need a purpose to be magnificent. It just needs time, space, and gravity. And from that, from almost nothing, you get stars, worlds and minds, capable of understanding where they came from. Which brings us full circle. You are made of matter forged in stars. You are the universe's way of looking back at itself. Not because some cosmic plan intended it, but because physics, given enough time, makes observers inevitable. Stars don't just light the universe, they make it knowable. And I hope that is something we can all feel grateful for. All right, that brings us to the end of today's lecture. We started with a simple question. Why do stars exist at all? And what we've found is that they exist because the universe had no other choice. Given gravity, given matter, given time, stars were inevitable. Not because anyone designed them, but because the rules of physics, followed for long enough, make them unavoidable. And once stars existed, everything else followed. Elements, chemistry, planets, life, thought. So before you go, let me leave you with one final idea. Every atom in your body heavier than hydrogen was created inside a star. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it forged in the cores of stars that lived and died billions of years ago. You are not just in the universe, you are made of it. You are the universe's way of understanding itself. And that's not poetry, that's physics. In a future lecture, we'll build on this foundation. We'll talk about what time actually is, not as a philosophical concept, but as a physical property of the universe. Why it only moves in one direction. Why we remember the past, but not the future. And what entropy has to do with all of it. But for now, take a moment. Think about what we've covered. Let it settle. Thank you for listening. I'll see you in the next lecture.